Let us begin now with this topic of kinematics. So the basic task here is to learn how to describe the state of a system, not from a classical point of view, but now from a proper quantum point of view. But we need to have a good solid definition so that we can begin our discussions. So I'm going to give you the definition for a state of a system. So here's my definition. I'm going to say that two identical systems. Now, by identical, what I mean here are, I'll have two systems. Maybe they have they each have two electrons and two protons in them, right? The system itself. I'm not talking about the state that it's in, but the components of the system have to be the same. They have to be identical. So two identical systems are in the same state. So that's what we're defining. And I'm going to say they're in the same state if. And if you want to be a mathematician, if and only if, here's the condition now, the results of all possible experiments now by experiment, what I mean here is what we would call measurement of an observable. And I want to describe what I mean by that, right? So an observable is something that we can actually, go out and measure. So I'm not talking about our impressions, about the feelings of an electron as we force it to travel through some slit. What I'm talking about here is something like you look in a microscope, you see the electron, you count how many tick marks are, it's next to the tick mark 16.3, and you can therefore determine its location and write down some quantitative value. So I want something that I can actually see in an instrument, and I want something that I can quantify. That's what I will mean by an experiment. So if the results of all possible experiments are yield for the two systems identical results, right? If there is some experiment out there that can get me different results from the two systems, well then clearly they are not in the same state. Now exactly what we mean by observable and measurement, that is going to take a little thinking, and we will look at that in just a moment. Before I get to that, I want to make a note here. I want you to note that the idea of the experiment may include a time delay before the actual measurement. But the time delay, of course, would have to be the same time delay for the two systems so that we're comparing apples and apples. So the experiment may include a time delay. And I guess what I really want to emphasize here, an equal time delay for the two systems, an equal time delay before the measurement. And I hope you can see that in this definition, the definition is constructed really to allow us to carry out science. Because in science, I need my experiments to be reproducible and to be predictable. The reproducibility comes about from the idea that once I have these two systems that are in the same state, right, I can reproduce exactly the same experimental results on the two systems. If they come out differently, I have to say they must not have been in the same state. Otherwise, if I believe my experiments can be different for two systems that are in the same state, there's nothing that's repeatable. The predictability part comes in from the idea of this time delay, right? If I now know they are in the same state, if life and the universe allows for prediction, as we're looking for in science, the predictability of behavioral patterns, right? I need to also be able to say something about the fact these systems are going to behave in the same way in the future. If two identically prepared systems give me different results after a certain amount of time, I have to conclude they must have been somehow in a different state. So that's my basic definition. Now, Again, I understand this is a little bit abstract, so I think the useful thing to consider to really nail down these concepts is to consider first the classical case, where we are more familiar with things, and then we can give good definitions for these various quantities, these various concepts. So the first concept to consider is what constitutes an observable in a classical system. Now, an observable, as we had said, is something that you can actually go out and see, right, and measure and quantify. So the observables in classical physics include things like the velocity of the various particles, but we've been learning we don't think in terms of velocities, we think in terms of momenta. Of course, the momenta of the various particles at a given time would be the thing we would observe. Are directly tied to the velocities, you would just multiply by mass. And the masses of the particles, notice, are I consider to be part of the setup of the system, right? I'm given a system with a certain set of masses in them. I know the masses. That's how I knew they were identical systems. But the state of that system would depend upon the velocities of those masses. Other things we can observe, of course, are the positions of those masses at a given time t. Other quantities we can certainly think about are things like the angular momenta of the particles that we can measure, and of course we know how those are defined. Some of the other quantities, you may measure the energy, say, of the system, the total energy, or what we like to think of as really the Hamiltonian. Well, if you can go and measure that. You can determine it if you happen to know all of the momenta and the potential function in terms of all of the positions of the particles. And there's a whole list of these things. But what I hope you're noticing is that there are really two categories of observables, right? There are these type of observables you can actually determine from a more primitive set of observables. The basic underlying set of observables in classical physics are the positions and the velocities. So those are our observables, and we have the sense of these more primitive observables. If we know these, then we know all of the other observables. So that's observable, the definition of observable. We also then have the idea of a measurement. And in classical physics, the idea of a measurement is so intuitive to us, we really don't give much thought to the distinction, in some sense, between the measurement and the observable. The distinction really is the observable is the thing that you go out and observe, right? And the measurement is when you quantify it. So the measurement in the classical case is basically go and find, say, the location of some particle. So you go and find something like, the position of the nth particle at time t. That's a fairly simple concept of a measurement.